So in this lecture, we will look at some few exercises which you all will require when we prove the Syllo's second and third theorems. Okay. So let's prove the first exercise. So suppose G is a group and G is an element in G, then we can define a very interesting function from G to itself, that is phi g of x equals gx G inverse. Okay, we will prove that this is an automorphism. If you don't know what is an automorphism is an isomorphism from a group to itself. Okay, an isomorphism is a 1-1 onto homomorphism. An automorphism is a isomorphism from a group to itself. Okay, so how do I prove that this is an automorphism? So firstly, I have got to prove that this is a homomorphism. So to prove it's a homomorphism, we start with we have to prove that phi g of xy is phi g of x times phi g of y. What is phi g of xy? Phi g of xy is gxy G inverse. Now we can multiply in the middle here by G inverse G to get gx G inverse times gy G inverse. But this is phi g of x times phi g of y. So this proves that the function is a homomorphism. Next, I want to prove that it is 1-1. So suppose phi g of x is equal to phi g of y. This will mean that gx G inverse is the same as gy G inverse. Now multiplying to the left by G inverse and to the right by G, we will get x is equal to y. So therefore phi g is a 1-1 function. Next, we need to prove that phi g is onto. Okay, you should try to stop the video here and try to think of the proof on your own. So onto, what is the meaning of onto? We start with any y inside G and we show that there is an element in G which maps onto it. So what would you expect to map onto y? See, suppose x maps onto y, what will happen? We'll have gx G inverse is equal to y, which means that what should x be? X should be G inverse yg. So that's the element that maps onto y. So you can clearly see that phi g of G inverse yg is G times G inverse yg times G inverse, which is y itself, and therefore the function is onto. Therefore you can see that phi g is an automorphism. Next, we will prove that if H is a subgroup of G and G is in G, then GH G inverse is a subgroup of G. Okay, and moreover, H and GH G inverse are isomorphic. That means there is an isomorphism from H to HG GH G inverse. Okay, this is very simple. This proof is very simple. Let's look at the image of H under phi g. What is the image of H under phi g? The above uh, function. What is this? This will be the set of all phi g of H such that H is in H. Okay, which is the same as GH G inverse such that H is in H, which is exactly the set G capital H G inverse. And since phi G is an isomorphism, H will be isomorphic to GH G inverse. Okay, so you can, so this is the proof of the theorem. So therefore, if H is a subgroup, then any conjugate of that subgroup is going to be isomorphic to H. Okay, which will give you many different things. You know that isomorphic structures look alike. Okay, they behave in a very similar way. Therefore, they will have the same number of elements and so on. Think of what is the isomorphism from H to GH G inverse. It is not very difficult. Try to think of it. Okay, so we say that two subgroups H and K are conjugates if we can write H as some GH genes, then they are conjugates. Okay, I will leave this out to you to prove that the relation on the set of all subgroups, say X is the set of all subgroups of G, X is set of subgroups of G, okay, then the relation H is related to K if K is a conjugate of H. Okay, this relation is a equivalence relation. Okay, so I will leave this proof out to you. You can very easily do it. Okay, now let us look at this particular subgroup. Given an element, given a subgroup H of G, let us look at the subset of G, NH, which is the set of all G in G, such that this particular conjugate, that is GH G inverse, is equal to H. Okay, so we will prove that this set here is a subgroup of G. Okay, and we will show that H is a normal subgroup of NH. Okay, I am not saying that NH is a normal subgroup of G. I am saying that H is a normal subgroup of NH, which is actually quite simple. Okay, so first, how do I prove that NH is a subgroup of G? Firstly, I have got to show that E belongs to NH. How do I show that E is in NH? What is EH, E inverse? This is H itself, which means that E is in N of H by the definition of NH. Okay, so E is in NH. Secondly, I need to prove that NH is closed under multiplication. So suppose you have two elements, say A and B in N of H. I need to prove that A times B is also in NH. So this will mean that A H A inverse is equal to H and BH B inverse is also equal to H, which means that AB times H times AB the whole inverse is ABH B inverse A inverse. Now this portion here, that is BH B inverse, is the same as H. So this gives us AH A inverse. And again AH A inverse is H, so we get H. And therefore AB is in N of H. So N of H is closed under multiplication. Let us now show that n of h is closed under taking inverses. So suppose A is in n of h, I want to prove that A inverse is in n of h. So since A is in n of h, we know that A inverse is equal to h. Multiplying on the left by A inverse and on the right by A, we get h is equal to A inverse h A, which is A inverse inverse. Okay, so here you can see that A inverse h, A inverse inverse is equal to h, which means that A inverse is in n of h. And this proves that n of h is a subgroup of G. Next, we need to show that H is a normal subgroup of G. If you don't remember what is a normal subgroup, please go back and look at the definition. Okay, the moment you know the definition and some equivalence statements, you know why n of h is why h is a normal subgroup in n of h. So to prove that it is a normal subgroup, let's start with some G in G. What do I need to prove? Sorry, I need to start with a G in n of h, because I am only proving that h is normal in n of h. Okay, so G in n of h. So start with G in of n. What is the meaning of this? This means that G inverse is equal to h. This means that multiplying to the right by G, that GH is the same as HG. Okay, which means that what I have proved here is, you give me any G in n of h, this left coset is the same as the right coset, which means that h is normal in n of h. Okay, so this proves our exercise. Okay, now this is what is a very, very important statement. This statement here will be used while proving the Sylow's theorem. So it's very simple also to prove. So if I look at all the conjugates of H in G, see this, the conjugates of H in G is going to be a set of the type, is going to be a set GH G inverse such that G is in G. I want to know the number of conjugates of H in G. These can repeat. You could have some G1H G1 inverse to be the same as G2H G2 inverse. Okay, but when will this be the same? That's the question. How many times they will be the same? So that is so when will they be the same? It will be the same only when multiply to the left by G2 inverse and to the right by G1, you will get G2, yeah, sorry, you multiply to the left by G2 inverse and to the right by G2, you get G2 inverse G1 H into G1 inverse G2 equals H, and that tells you that G2 inverse G1 H into G1 inverse G2, sorry, this is so this is the same as G2 G1 inverse sorry, G2 inverse G1, the whole inverse is equal to H. What does this mean? This means that G2 inverse G1 is in N of H, which means that you can see back in the definition, this is some x h x inverse is equal to x, which means that x is in N of H. So this means this is here, and therefore G1 is in the left coset G2 N of H, and therefore this means that G1 N of H is equal to G2 N of H. Okay, so when are these two equal? When G1 N of H is equal to G2 N of H. In fact, you can go back in the same direction and you can prove that these two cosets are equal when these two conjugates are equal. Okay, so let's prove this theorem now. So let C be the conjugates of N of H. Sorry, the conjugates of H. The set of. Okay, now what I want to do is I want to show that the number of conjugates is G by N of H. That means I want to set up a bijection F from G by N of H to C. Okay, so we will set up the bijection as F of, take any G times N of H, to, or we could set it up in the other direction. It does not make a difference, but since I have proved the other way, I will do it this way. So C2 N of H to G by N of H by F of any conjugate will look like G H G inverse. I will take it to the right coset G times N of H. Now firstly I want to show that F is well defined. Okay, and to prove that F is well defined, I want to say that if two conjugates are the same, then the corresponding left cosets of N of H are also the same, which is this proof here, what I have written. Okay, so this is the proof for well defined. Next, I want to show that F is 1, 1. How do I prove that F is 1, 1? So suppose G1 times N of H is equal to G2 times N of H. What is the meaning of this? We can just go in the opposite direction, okay, and we will have G1 is in G2 times N of H, which means that G2 inverse G1 is in N of H, okay, which tells us that if this is in N of H, it means that G2 inverse G1 times H times the inverse of this. What is the inverse of this? This is G1 inverse G2 is equal to H. So this is in N of H, this happens. This means that multiply to the left by G2 and to the right by G2 inverse, we will get G1H G1 inverse is equal to G2H G2 inverse. So I've started with the I've said that these two images are the same, so therefore this tells me that the two elements should also be the same, and therefore the function f is 1, 1. Proving that the function is onto is a triviality because what do elements in G by N of H look like? So they look like G times N of H, right? Where G is in G. What will map onto G times N of H? The element that will map onto G times N of H is GH G inverse. By the definition, this maps onto G times N of H. And therefore, given any element in the codomain, there's an element from the domain, because GH G inverse is in the domain, which maps onto it, which means that F is also onto. Therefore, F is a bijection, and the number of elements in the C is the same as the number of elements in G by N of H. And that proves our theorem. Okay. Now, this is also another important exercise which will be used in the zero theorems. So, we are going to prove that if X is an element of Nk, okay, K is a P-zero subgroup. If X is an element in Nk, that is a power of P, then X has to be in K. So all the powers of P, all the elements whose orders are powers of P in Nk cannot lie outside of K. K is here, N of K is bigger than that. K is a subset of N of K. So this will be your N of K. And G is the group which is bigger than that. Right? So if X is an element that lies in this region here, such that the order of X is a power of P, then we are saying that it cannot be in this portion. It can only be in K. So that's the proof. That's what we are going to prove. So let us try to prove this theorem. So suppose the order of K now K is a P-zero subgroup, which means that it is of order P raised to N. Okay. And this means that, so the order of K is P raised to N, which will mean that the order of G, so therefore the highest power of P that divides the order of G will be P raised to N. This will be P raised to N times M, where P does not divide M. Okay, now as N of H is a subgroup of G, N of H is a subgroup of G, therefore by Lagrange's theorem, the order of N of H divides the order of G. Also, H is a subgroup of N of H, okay, which means that the order of H divides, this is K, okay, so the order of N of K, the subgroup is N of K is a subgroup of G, and K is a subgroup of N of K. So the order of N of K by Lagrange's theorem again is a multiple of the order of K, but the order of K is P raised to N. Okay, so therefore the order of N of K will be some P raised to N times R. Okay, where where P cannot divide R in fact. Okay, so why P cannot divide R? Because P raised to N times R should divide P raised to N times M, which means that R should divide M, and since M P does not divide M, P cannot divide R. So that will tell us that P cannot divide R. Now what is the order of the group N of H by H? So N of K by K. So what is the order of this? The order of this is R, and therefore the order of X times K, X times K, the order of X times K will divide R, which means that X times K raised to R belongs to K raised to R. X times K raised to R will be equal to K, because that's the identity element. Okay. This will divide R, which means that X times K raised to R which means that X raised to R times K will be equal to K, or in other words, X raised to R will belong to K. But we want to show that X belongs to K, not just X raised to R belongs to K. We also know that X is a power of P. Say the order of X is P raised to S. Okay, which means that X K, the whole raised to P raised to S, will be equal to X raised to P raised to S times K. But X raised to P raised to S is identity, which gives us K. Okay, so therefore the order of X times K will divide P raised to S. Okay, and you can see two things here. One is the order of X raised to K divides R, and the order of X raised to of xk divides P raised to S. But we know that P does not divide R, which means that the only divisors of this are 1, P, P square and so on. And the divisors of R is not P. P does not divide R. Therefore, the only common divisor of R and P raised to S is 1. So therefore, this tells us that the order of X raised to K is 1. So the order of xk is 1, and the meaning of that is that xk is equal to k, or in other words, x belongs to k. You can see this calculation here was not actually required. Okay, so this proves this theorem. Finally, we will prove that if phi is a homomorphism from G to K, group homomorphism from G to K, and H is a subgroup of G, then phi G, the order of phi G divides the order of, the order of phi H divides the order of H. Okay, so we will prove two things. One is that phi of H is a subgroup of K, which we must have proved earlier. And secondly, the order of phi H divides the order of H. So to prove that phi H is a subgroup, we have to first show that it contains the identity element. So let E be the identity element, identity in G, and E prime be the identity element in K. I will first show that E prime is in phi of H. So this is simple. We know that H is a subgroup of G, which means that E belongs to H. Because it's a subgroup, it contains the identity element, which means that phi of E is in phi of H. So I will show that phi of E is equal to E prime. Let us see how to prove that. So phi of E is the same as phi of E times E. This is a very standard calculation to use, which is phi of E times phi of E multiplying by the inverse of phi of E on both sides, because phi of E lies inside phi of H, which is in K, and K is a group, so every element contains an inverse, so we can multiply by the inverse of phi of E on both sides to give us phi of E is equal to E prime. Okay, and therefore E prime is in phi of H. Phi of E is in E prime. Sorry, phi of E is in phi of H. So therefore E prime is in phi of H. So phi of H contains the identity element. Next, we want to prove that it is closed under multiplication. This is very easy. So suppose we have some x and y in phi of H. This will mean that there exist A and B in H such that x is equal to phi of A and y is equal to phi of B. This means that x times y is equal to phi of A times phi of B, which is phi of AB. But we know that H is a subgroup of G, which means that H is closed under multiplication, which means that AB is in H, and if AB is in H, phi of AB is in phi of H, and therefore xy is in phi of H. Next, we will show that phi of H is closed under taking inverses. So start with any x in phi of H. I want to prove that x inverse is also in phi of H. So this means that there exists some A inside H such that x is equal to phi of A. Now, what is the inverse of x? Okay, the inverse of x will actually be phi of A inverse. So let us show that. So multiply to the left by phi of A inverse. We will get x times phi of A inverse is equal to phi of A times phi of A inverse, which is phi of A times A inverse, which is phi of E, but phi of E is E prime. We have proved that here, that phi of E is E prime. Okay, and therefore multiplying by the inverse of x on both sides, we will get phi of A inverse is equal to x inverse. So x inverse is phi of A inverse. But A inverse is in H, as H is a subgroup and A belongs to H. A inverse is also in H. So therefore, x inverse will belong to phi of H. So this proves that phi of H is a subgroup. Next, we want to prove that the order of phi of H divides the order of H. So let's look at how we can prove that. Okay, so this proof is simple if you okay, let's not say that. So let's say, let us take the set S to be the set of all x in H such that phi of x is equal to E prime. Now, since phi of h is finite, I can write phi of h as b1 equals E prime, b2, the distinct elements up to say bm. Okay. Now, for each of these are all images of the set H. Okay. So, for each of the I, there will be some AI in H such that phi of AI is equal to Bn. Okay, so this is what we are going to take, and we will look at this set, that is the set let's say we will call it as X. We'll take X to be the set S, which is phi of A1, okay, because phi of we could in fact even fix A1 to be the identity element. That will make it easier for you. S of A2 up to S of AM. Okay, now what I'm going to do is I'm going to prove that these are all right cosets of S, and therefore they all have the same number of elements as S. So I am going to prove that H, okay, I'm going to prove that H is partitioned into these sets, that is SA1, SA2, SAM. So one of them is SA1, another one is SA2, another one is SA3, and so on. So what will this mean? This will mean that the number of elements in H is the sum of the number of elements in each of them. So that but all of them have the same number of elements as S. So that will be M times the number of elements in S. But M is the number of elements in phi of H. So this is number of elements in phi of H times the number of elements in S, which means that the number of elements in phi of H divides the number of elements in H. Okay, so that is how we are going to go about this proof. So how to prove that this partitions S? First thing that we need to prove is, if we take any element in H, we need to prove that it is in one of these. So start with some H in H. So if H is in H, you can see phi of H is only this finite number of elements. So therefore, phi of H will be equal to some Bi. Okay, but Bi is phi of Ai. Using the fact that phi is a homomorphism, this will give us phi of H times phi of Ai whole inverse is equal to E prime, which is, but phi of Ai the whole inverse is nothing but phi of Ai inverse. So this is H times phi of Ai inverse is equal to E prime. But this here is phi of H times Ai inverse, which means that H times Ai inverse is in S, or in other words, H is in S times Ai. So you can see that given any H in H, it will be in one of these. Okay, so Next, we need to prove that there is no intersection between two of these, between any two of these. Okay, they are all distinct right cosets. So to prove that, we'll need to wipe this out. So suppose SAI is the same as SAJ. What is the meaning of this? This will mean that AI times AJ, the whole inverse, is in S. But what is S? It is the set of all points whose image is the identity element. So therefore, this means that phi of AI times AJ inverse is E prime. Okay, using the fact that phi is a homomorphism, we get phi of AI times phi of AJ inverse is equal to E prime, which means that phi of AI is the same as phi of AJ. But this means that BI is the same as BJ. But those were distinct elements in phi of H. So therefore, this means that I should be equal to J. Okay. So what have I proved is that if any two of these sets are equal, it would mean that AI is equal to AJ. Okay. That essentially says that none of these can be equal, because I have taken, or that means that I is equal to J. That's what we prove. But that is not possible, and therefore these have to be all distinct, and hence the cardinality of H will be M times the cardinality of S, because each of them have cardinality S, and that is cardinality of phi of H times cardinality of S. So therefore the order of phi of H divides the order of H. Okay, so for the last exercise, we will show that the number of conjugates of H in G is G by N of H. And as you would expect, to prove this, we will set up a bijection. So we will define F from the set of conjugates of H in G. Let us call the set of conjugates of H in G as C to G by N of H, where we will take a conjugate of H will look like GH G inverse. So this we will take to the left coset of N of H. Now we have to prove that this function is well defined, because two of these conjugates could be equal. So suppose G1H G1 inverse is the same as G2H G2 inverse. What is the meaning of this? This means that multiply through on the left by G2 inverse and on the right by G2, will get G2 inverse G1 H times G1 inverse G2 is equal to H, which means that G2 inverse G1 times H into G2 inverse times G1, the whole inverse, equals H. Okay, what does this mean? This means that G2 inverse G1 is in N of H. Okay, which means that G1 is in G2 times N of H. Or in other words, G1 times n of h is equal to G2 times n of h. Okay, so this proves that the function is well defined. Next, we want to show that the function is 1, 1. So to prove that the function is 1, 1, we suppose that f of G1h G1 inverse is equal to f of G2h G2 inverse. What is the meaning of this? This means that G1 times n of h is equal to G2 times n of h. Just in the reverse direction of well defined, this will prove that G2 inverse G1 is in n of h, which would mean that G2 inverse G1 h into G2 inverse G1, the whole inverse, equals h, which would mean that multiplying on the left by G2 and on the right by G1 inverse, we will get G1h G1 inverse is equal to G2h G2 inverse. So this proves that the function is 1, 1. Now how do we prove that it is onto? To take any element in this, the element will look like G times n of h. What will map onto it is the conjugate of h, G inverse. So therefore, that will prove that the function is also onto. Hence, the function is a bijection, which means that the number of elements in C is the number of elements in G by h. So this proves our exercise. Thank you.